VIN Future
Recording
Prize,
in
a new
progress.
global science and technology prize for humanity from Vietnam. One VIN Future grand prize of $3 million. 3 additional special VIN Future prizes valued at $500,000 each. VIN Future Prize honors science and technology work that creates or has a high potential to create meaningful change in the everyday lives of millions of people. Join us to make a change for a better future.
Welcome to the August InnovaTalk webinar titled A Green Future of Hydrogen Economy. My name is Tao Chen, and as always, it is a pleasure to be your moderator for today. We are so thrilled to have each and every single one of you present in today's webinar as we embark on the journey to discover more about the potential of hydrogen in its process to gaining net zero. Well, without further ado, please allow me to introduce to you our panelists for today. Well, Professor Vivian Yam, Chair Professor of Chemistry at the University of Hong Kong, member of the VIN Future Prize Pre-Screening Committee, Professor Vivian Yam will be the chair for today's webinar. Professor Nigel Brandon, Dean of the Faculty of Engineering at Imperial College of London. Professor Brandon will be our first distinguished speaker for today's webinar. He was awarded the title of Officer of the Most Excellent Order of the British Empire, rewarding contributions to the arts and sciences, work with charitable and welfare organizations, and public service. Our second distinguished speaker is Professor Kazunari Domen from the University of Tokyo, Japan. With close to 50 years of experience in the energy research industry and significant investment in his projects, Professor Domen promises to deliver valuable and fresh insights as one of the keynote presenters at today's webinar. And last, but definitely not least, our representative of the Vietnamese energy community, Mr. Ha Đăng Son, Deputy Chief of Party Technical of the Vietnam Low Emission Energy Program 2, a 5-year activity funded by the U.S. Agency for International Development. Well, before we get to officially meet with our panelists for today's webinar, I would like to invite you all to keep watch for a short trailer that serves as a great discussion ahead. Please take a look.
Hydrogen is the lightest and simplest element in the universe, yet incredibly abundant. In fact, the sun, the source of our heat and light, is comprised mainly of this remarkable element, alongside helium. But hydrogen isn't just important for cosmic reasons. It is essential for life on Earth, being present in almost all molecules, within living things and in every drop of water we drink. Did you know that hydrogen is a versatile energy carrier that can be transformed into either a liquid or gas form, providing a clean and efficient source of power for a range of applications? Perhaps even more exciting is the potential of hydrogen to spearhead our shift towards a sustainable net zero future. It's quickly becoming known as the gateway to a green economy, paving the way for a future of reduced reliance on fossil fuels. And that's why we're thrilled to announce that the VIN Future Foundation is bringing you an unmissable event, our August InnovaTalk webinar, A Green Future of Hydrogen Economy. Join us as we delve into the groundbreaking research, innovations, and ideas that will shape the future of our planet. Get ready to meet our incredible chair for the upcoming webinar, the one and only Professor Vivian Yam. Prepare to be dazzled by the brilliance of Professor Vivian Yam, a powerhouse in the fields of chemistry and energy. As the esteemed Chair Professor of Chemistry at the University of Hong Kong and a member of the VIN Future Pre-Screening Committee, she will bring an incomparable depth of experience and expertise to the table. Featured as our first distinguished guest is Professor Nigel Brandon, Dean, Faculty of Engineering, Imperial College London. His research focuses on electrochemical devices for energy applications, with a particular focus on fuel cells, electrolyzers, and batteries. He was awarded the title of Officer of the Most Excellent Order of the British Empire, rewarding contributions to the arts and sciences, work with charitable and welfare organizations, and public service. Our second distinguished guest for the webinar is Professor Kazunari Domen, whose career has been spanning almost half a century. Professor Domen has dedicated his life to developing water-splitting photocatalysts and has become an internationally respected scientist and researcher. His groundbreaking research has resulted in numerous prestigious publications and over 102,000 citations. Last but definitely not least, our representative for the Vietnamese energy community is Mr. Ha Đăng Son, Deputy Chief of Party Technical of the Vietnam Low Emission Energy Program 2. Prior to V-LEEP II, Mr. Sun served as a Green Growth Advisor to the Ministry of Planning and Investment, where his work focused on supporting the development of green growth action plans for key provinces in the country. Are you ready to unveil the incredible transformation that hydrogen can bring to our world on our journey towards achieving a net zero future? Have you ever wondered about the safety aspects of harnessing hydrogen's power in our everyday lives? This is your golden opportunity to uncover the answers to your questions at the VinFuture Foundation's InnovaTalk webinar, A Green Future of Hydrogen Economy.
And now, ladies and gentlemen, it is my distinct honor to introduce to you our chair for today's webinar, Professor Vivian Yam. She is a distinguished figure in the field of chemistry who brings an extensive range of expertise from the University of Hong Kong. It is also noteworthy to mention that in 2023, Professor Yam became the first Asian chemist ever to be awarded the prestigious Baylor Medal, which has been established for over 50 years. We're privileged to have Professor Yam guiding us through the enlightening discussions of today's webinar. And without further delay, I humbly pass the virtual stage to you, Professor Yam, as we eagerly await your insights and guidance.
So thank you very much for introducing the topic. So we have a very exciting webinar today, A Green Future of Hydrogen Economy. And as you can see in the trailer video and all that, there's no more need for me to explain a bit more about why hydrogen is so important, right? It's a global issue. We have really leading experts here today, both from the perspective of coming from electrochemical energy, converting to hydrogen, giving hydrogen, producing, as well as photocatalysis to split water to hydrogen. So we're really all very excited here. And I would like to give a much sort of detailed introduction of our distinguished speakers and also the panelists. So first I introduce again Professor Nigel Brandon. Of course, he's Dean of Engineering in Imperial College London. He holds the chair in Sustainable Development in Energy, as well as the Dean of Faculty of Engineering, as I mentioned, in Imperial College London. Now, his research is focused on the science and engineering of electrochemical technologies for the low carbon energy transition, with a particular focus on fuel cells, hydrogen, and flow batteries. He was the director of the UK Hydrogen and Fuel Hub from 2012 to 2022, and is the chair of Imperial Sustainable Gas Institute. He's a fellow of Royal Academy of Engineering, a fellow of the Royal Society, and an overseas member of the US National Academy of Engineering. He's also the founder of the UK fuel cell and electrolyzer company, Ceres Power, and a founder and chairman of the UK flow battery company, RFC Power. So he's really a giant in this field. The second distinguished speaker is Professor Kazunari Domen. So Professor Domen started his professorship at the University of Tokyo in 2004 and was cross-appointed at Shinshu University as a special contract professor since 2017. He became university professor of University of Tokyo in 2019. His research interests include heterogeneous catalysis and materials chemistry, with particular focus on surface chemistry, reaction dynamics, photocatalysis, solid acid catalysis, and mesoporous materials. Recently, his efforts have focused on development of photocatalysts for water splitting and construction of practical solar hydrogen production system. He has published more than 800 articles with over 90,000 citations and an H-index of over 139. We also are happy to have Mr. Daihan Sun here with us. So Mr. Sun is the Deputy Chief of Party Technical of the Vietnam Low Emission Energy Program 2, V-LEEP II, a 5-year activity funded by the U.S. Agency for International Development, with the primary goal of assisting Vietnam in advancing the transition of the nation to a clean, secure, and market-based energy sector. So prior to V-LEEP II, Mr. Sun served as a green growth advisor to the Ministry of Planning and Investment, where his work was focused on supporting the development of green growth action plans for key provinces in the country. So it's an extremely important figure here for helping us to build a green economy, particularly for Vietnam. And so without further ado, may I now invite Professor Nigel Brandon to deliver your presentation. So we very much look forward to the very exciting work of you. So Nigel, please.
Okay, thank you very much indeed. And I think the colleagues are going to share my slide deck very shortly. So I've been going to talk to you today about some of the work I've been involved in terms of electrochemical technologies and the role they can play in the low carbon energy transition. It's a field I've been working in all of my career, but I don't think I've ever seen a time at which people are more interested or the work is more relevant than today. So next slide, please. So in the time I've got, I want to very briefly talk about why this topic is of interest and is relevant to the energy transition, both in terms of electrochemical technologies and hydrogen specifically. And I'm going to focus my time then on two areas where I've been most involved. One is around solid oxide fuel cells and solid oxide electrolyzers, and the other is around flow batteries, and specifically a novel type of liquid gas flow battery that uses hydrogen as one of its storage vectors. And then just very briefly summarize at the end. The theme of my work really is taking research out of university labs and into commercial application and hopefully then subsequent deployment to have impact. That's the kind of the theme of what I'm trying to talk about in this context. Okay, next slide, please. Okay, next slide, please. Now, every country has a different energy context, and just to kick this presentation off, I'll just refer to the UK, which is obviously where I'm based. And this is the flow of energy through the UK energy system. The red line at the bottom there is the flow of energy as electricity. And we've made quite good progress in decarbonising that. And the intent, of course, is to continue to decarbonise that vector, which I think will become an increasingly important over time, as it will be the electricity generated from low carbon sources like wind and solar, or in some countries, nuclear. The slightly jagged horizontal line in the middle in grey is the flow of energy as liquid fuels, which is almost entirely today fossil-based and almost entirely for transport applications. And there are opportunities to displace that with electricity and replace fossil-based combustion engine vehicles with battery electric vehicles. And potentially for some areas then also hydrogen fuel cell electric vehicles. And then the top line, the biggest line, which has the sinusoidal shape, is the flow of energy as natural gas. And in the UK context, this is, as you can see clearly, our biggest energy flow, and yet and mostly used for heat, both industrial and buildings, but also for power. And the cyclical nature of that between the low in the summer and the high in the winter shows you the scale of the heat demand. And it's really, how do we replace that natural gas with a zero carbon or a very low carbon carrier? That's one of our major challenges. And it's here that hydrogen comes in, because it's really hard to conceive of a system in which we move entirely away from liquid fuels and natural gas into electricity without conceiving of having some energy carried as molecules. And if we're going to carry that energy as molecules, the easiest molecule to make is hydrogen. Though, of course, having made hydrogen, we can use it subsequently to make other things like ammonia, or can recombine it with, say, biogenic CO2 into liquid fuels. But I'm going to focus today on the hydrogen aspects and the role of electrochemical technologies, which are particularly well versed at both taking electrons and turning it into molecules, and taking molecules and turning it into electrons. And that's why they sit and will play such an important role in the transition going forward. Okay, next slide, please. Now, of course, we use hydrogen today. We make about 100 million tons of hydrogen globally, and it's pretty much entirely made as a chemical feedstock. It's used in the synthesis of ammonia fertilizers, in chemicals and in petrochemicals. The situation going forward is, of course, to replace that hydrogen, which is primarily sourced, 96% of it is sourced from natural gas and coal, and to replace all of that hydrogen with hydrogen sourced from low carbon sources, but also to expand the role of hydrogen as an energy carrier and not just as a chemical feedstock. Okay, next slide, please. So this is a sort of cartoon of the role hydrogen might play in the future, and I'm showing here green and blue hydrogen. It comes out of a paper we wrote some years ago, and it simply shows that you can, in cartoon form, that we can make green hydrogen by electrolysis, and we can store and use that hydrogen. And whilst not the focus of my talk, we can make blue hydrogen from fossil, or indeed from biomass with carbon capture, store that CO2 and then use that blue hydrogen. My talk today is going to be about the green hydrogen piece, and of course that's the focus of this webinar as well. But it shows the interconnected nature of a future system with electricity and molecules flowing together and interacting and coupled together, and the need in this space to think about how we make, distribute, store, and use hydrogen and as an energy carrier. Okay, next slide, please. Now, we're not going to, I'm happy to talk about cost in the Q&A. I'm not going to talk about it any further other than to say that the price of green hydrogen is extremely sensitive to the price of the renewable electricity or the low carbon electricity used to produce it. Some 60 to 80% of the cost is dependent on that power price. Of course, the capital cost of the electrolyzer matters as well. But the amount of electricity we use and the cost of that electricity is therefore the key cost driver for green hydrogen cost. Next slide, please. Now, this is a figure that comes from some nice work from a German group in Munich. And it's a review of different electrolyzer technologies, and this chart kind of summarizes some of the key points. As shown on here is the AEL, that's the alkaline electrolyzer. That's the most widely available and most mature electrolyzer technology today. And if you go and look out at some of the global world-scale electrolyzer projects being built, they'd be built with that particular type of technology. The horizontal axis there shows current density. Current density is a measure of the amount of hydrogen we produce per unit area of our electrolyzer, and the higher the current density, the smaller the electrolyzer. So that impacts capital cost fundamentally. And then the vertical axis is efficiency. And obviously efficiency is a critical factor in determining the amount of power we need per kilogram of hydrogen we produce. And you can see that alkaline electrolyzers have a relatively low current density. That means they're quite large pieces of equipment, and they have a sort of modest, today, about 65% efficient technology, with the review paper here suggesting that a very low, you could get higher current densities if you wish, but you pay a penalty in current density. Higher efficiency, sorry, you would pay a penalty in current density. The PEMEL is the PEM electrolyzer. That's a relatively new technology, but now commercially mature. Which uses precious metal catalysts. It uses more expensive materials. It uses iridium, which is a very rare material. But it does deliver you high current densities, and it delivers similar efficiencies to the alkaline electrolyzer. But it has some characteristics in terms of ability to produce hydrogen at pressure more flexibly and more compactly. Now, the technology I am particularly interested in is the red one there, the SOEL, which is the solid oxide electrolyzer. And why am I interested in it? Because of that very high efficiency that it can achieve. And in fact, you'll see there efficiency is quoted over 100%. As I'll explain in a moment, of course, one can never really achieve 100%. So it depends on how you're defining efficiency. But nonetheless, one can get very high efficiencies with this technology. But it's not yet a mature technology, and it's not yet commercially available. But that's the area I'm going to talk about. So next slide, please. So in a solid oxide electrolyzer, the top left bit of thermodynamics there shows you that as you go up in temperature, whilst the total enthalpy, the amount of energy you need to split water, remains the same, the distribution of that energy between Gibbs energy, so the electrical energy demand, and entropy, so the heat demand, varies. And as we go up and up in temperature, we can need less electricity and more heat to split water. So as a heat is generally cheaper than electricity, and often available as a byproduct of other processes, that gives us the opportunity to get very high electrical efficiencies, and indeed apparent efficiencies which can exceed electrical efficiencies which exceed 100%. In practice, of course, that's because we're discounting the heat that's needed. We always need the same amount of energy, we're just using less electricity to get that product. But we can get very high electrical efficiencies, well over 90%, in what's called thermoneutral mode, where the temperature, where the losses within the electrolyzer balance the heat demand at the endothermic water splitting reaction. So we have a nice flat temperature profile and an extremely high electrical efficiency, and that's what's attractive when 60 to 80% of the cost is the cost of the power. Next slide, please. So I've talked there about electrolyzers. I'm also going to talk about fuel cells briefly, and a fuel cell and an electrolyzer are essentially the same thing running in different directions. I'm going to talk about the solid oxide fuel cell, which is the one on the left there, in which we have an oxide ion conducting ceramic electrolyte, and in fuel cell mode, air on the cathode and a fuel gas like hydrogen on the anode. In this embodiment, then we're going to strip electrons off the air on the air side, on the cathode side. We're going to create an oxide ion, which is going to transport across the membrane, which is then going to combine with the fuel molecule, in this case hydrogen, to produce steam and release electrons. And those electrons are going to go around an external circuit as current. And we're going to generate a voltage, which is dependent on the Gibbs energy of reaction. So typically, if there was no current being drawn in, but just over a volt per cell, and when we draw in current, it would fall down to perhaps 0.6 to 0.7 volts. So in this way, we produce power. And a fuel cell is the most efficient way of producing power from a fuel, far more efficient than the heat engine. And most importantly, it delivers that efficiency pretty much regardless of the size of the device. So they're very useful devices for producing electricity at high efficiency at length scales of perhaps, or power ranges of a kilowatt to a megawatt. So ideally suited for things like distributed generation applications where we embed power generation within the grid rather than large central power stations as it's commonly done today. Okay, next slide, please. I should stress that you can now buy fuel cells. If I was giving this talk a few years ago, that wouldn't be the case. This comes from the most current version of the Fuel Cell Industry Review, which is a very useful and public open document, which looks at where the sector's going. And one can see that once we're starting to ship significant amounts of power capacity now globally, though still small in the context of the global energy industry, but nonetheless commercial products are available. Next slide, please. And the next slide, please. So I'm going to talk now about the solid oxide area, which, as I said, is in the context of electrolyzers, gives this potential very high efficiency. And as I mentioned, the electrolytes here are ceramic. And whenever one is engineering products out of ceramics, one has to pay great attention to the thermomechanical stability of the device, how it's mechanically supported. And there are three broad approaches, and I don't have time to go into them in any detail, but they all depend essentially on the type of mechanical layer that is provided to support the electrolyte. The anode supported is the top shown there. Lots of companies developing that. The electrolyte supported, if you go to somewhere like Bloom or Sunfire, that's the type of technology they're developing. But I want to focus on the bottom, which is a metal supported design. And that's the design we pioneered in our work at Imperial College, and which has subsequently been taken forward commercially by this company, Ceres Power. Next slide, please. So in a typical electrolyte supported cell, just to show you we have a dense electrolyte, which is a ceramic. In an electrolyte supported cell, perhaps that might be 100 to 150 microns thick. In an anode or metal supported cell, more like 10 to 20 microns thick. And then you can see some layers on the air electrode there, two different microstructures, a high surface area structure to give us catalytic activity in the area of the electrolyte, and a more coarse structure to give us gas transport, and the same then on the steam side. Again, you can see different microstructures to engineer different levels of electrocatalytic activity. Next slide, please. So we, back in the late 90s, we had a research grant. Off that research grant, we filed a patent on this metal-supported concept, which was new, and we formed a company to take that forward out of the university research. Next slide, please. That was 23 years ago. Where is it today? So this is some photographs from the company today, and the top left there shows a metal-supported cell without the air electrode on top of it. But you can see the metal support now is in a kind of engineered frame with various alignment holes and gas distribution ports. There is a nickel based anode in contact with that metal, and then the shiny layer you can see is a very thin 10 micron thick, also electrolyte. Next slide, please. And when one looks at that in any detail, and this is public information, one can see the different layers that comprise the cell. And again, I haven't got time to go into all of the details here, but if anyone's interested, we can pick it up in Q&A. But the key advantage of the metal-supported cell is that is really in that bottom left. And what it does, it allows you to make much more low-cost and effective seals between the cell and the interconnect plates that are used to join one cell to the next. And one of the big challenges in this area of high temperature materials is how do you ensure gas-tight seals that can tolerate and withstand the temperature cycles of going from cool to hot to cool that are necessary within the operating period of the device, and the thermal expansion changes that come with this. So the ability to use a welded seal and also a compression gasket seal on the other side, because of the temperatures here are much lower than they're around 600 C. It really gives this device a lot of mechanical stability and integrity. Sorry, just had a Teams call coming into my laptop. And so that's one of the key advantages of the approach. And all of the material science that's taken place over the last 20 years is all about how do we engineer a stable, robust, and manufacturable set of materials to deliver the performance we need. Next slide, please. Where's the company today? It's now listed on the London Stock Exchange. It's a $700 to $800 million business in terms of capital value, and is developing both electrolyzer technology currently being built to go to India, but also fuel cell technology in Japan, in Korea, in China, and in Europe. Next slide, please. And this is the photograph of the recent listing on the London Stock Exchange. Next slide, please. In terms of our own work, and again, haven't got a lot of time to go into it, we remain very interested in the research base and looking at microstructures, electrode design, and the next slide, please. And the supporting modeling and analysis work that go into that. Okay, next slide, please. So I want to now move on to energy storage, and I don't have a lot of time left, but just a few minutes to talk about that, and particularly longer term energy storage. It's fine, keep going with the slides. And I think so this is a picture from a UK context, and it just shows the scale of energy storage we'll need if we go with a wind-based renewable energy system, and the amount of energy storage we need to buffer periods in which the wind doesn't blow in the winter, which is very common in Northern Europe, where you're dealing with tens of terawatt hours of energy storage that one's needed. Next slide, please. And one way to think about that is to store hydrogen underground in appropriately engineered caverns. The scale of storage we need in the terawatt hours really can't be delivered with things like pumped hydro. This is one of the small number of pumped hydro facilities we have in the UK. It stores 9 gigawatt hours. So we need about 3,600 of these to deliver the level of energy storage we need for a wind-based energy system. Okay, next slide, please. And so there's been some good work done. Again, this is out of Germany, looking at the capacity for underground hydrogen storage across Europe. And the bottom line is that there is plenty of capacity, but it's not uniformly distributed. You need the right sort of salt cavern capability to be able to do that. Next slide, please. And the other type of longer term storage, which is the one we've been focused on, is this market for backing up things like solar photovoltaics with kind of 8 to 10 hours of energy storage, which is what a lot of studies predict will be needed in greater demands in regions where solar photovoltaics dominate. Next slide, please. And an attractive technology option for this is the flow battery. And this is the most conventional and currently available type of flow battery. It's called a vanadium flow battery, in which we store charge in a liquid electrolyte by changing the oxidation state of that electrolyte. And we form a reducing agent and we form an oxidizing agent in liquid form, and we store those in tanks. And by storing more electrolyte in bigger tanks, we can store more energy. And so this type of technology becomes attractive as we need to go to longer and longer periods of energy storage in this, and 8 to 10 to 24 hours is typical. So next slide, please. But vanadium is expensive. It's also available primarily from China and Russia, which creates some security concerns and supply concerns. And its price point is very volatile. So we have been pioneering a new type of flow battery, which is referred to here as the hydrogen manganese hybrid flow battery. It uses a manganese liquid couple, which you can change the oxidation state of, and hydrogen stored at relatively low pressures in a closed loop. And is a technology that would interface very nicely with a hydrogen economy if that grows, but can also be engineered in a standalone form. Manganese is not an easy system to use, and we've had to develop some new breakthroughs in how you stabilize that manganese solution to present the precipitation of manganese dioxide over time, but we've succeeded in that. And this technology is patented. Next slide, please. Is patented and has been taken out into a company. This is a much newer company. It's got 10 employees today, but Ørsted have just put this technology, chosen this technology from a very large field of 150 competing options for evaluation. So it's an exciting, a sort of exciting journey. Next slide, please. Thank you. And the next slide. So I'm running out of time. Let's recognize that hydrogen has its challenges around cost, around safety, and around energy density, but it also has its advantages. But one of the things we have to ensure also and recognize, next slide, please, is that it has some environmental impacts. So there's a lot of work at the moment looking at the environmental impact of hydrogen. So whatever we do, we need to build systems that don't leak, and we need to pay appropriate attention to the efficient generation, storage, distribution, and use of hydrogen. And the next slide, please. And so these are two recent studies looking at the global warming potential of hydrogen. It's definitely less than methane, but it's not zero. So we need to pay attention to it. Next slide, please. And as I said, just to close, then it's the intersection of molecules and electrons that are important. My time is going off telling me I've finished. And so we should, of course, stick with electrons where we can, but if we can't, then hydrogen's the next thing to use. And what I hope I've very briefly shown you is that electrochemical technologies like fuel cells and electrolyzers are a key, efficient and flexible way of converting between these two energy carriers. And indeed, that there is a great opportunity for international collaboration in this space. So with that, I will close. Thank you very much, and look forward to the questions to follow. Thank you.
So thank you very much, Nigel, for a very informative, even though it's very brief because of the time constraint, but we learn a lot from you. So probably we'll delay the discussion at a later stage. And now let me turn to our second distinguished speaker, Professor Kazunari Domen, to deliver his presentation. So Professor Domen, please. Um,
Can you see my slides?
yes.
Is it okay?
Yeah. And then a slideshow. Yeah.
Okay.
Okay. Thank you.
Okay, thank you very much. The title of my talk today is Photocatalytic Water Splitting for Solar Hydrogen and Fuels Production. Here I show the content of my talk. As a brief introduction, at first I like to discuss about the particulate photocatalyst for water splitting reaction. Then I move to the photocatalyst sheet and water splitting panel. After that, I like to introduce our recent attempt for the construction of a prototype solar hydrogen production system. Then I will summarize, and then I discuss a little bit about the further development of solar fuels. As first introduction, green hydrogen from pure water is one of the most promising energy source in the future. And at present, the solar cell or photovoltaics and the electrolyzer system is the most realistic system. But unfortunately, the cost of the hydrogen produced by this method is still more expensive than that obtained from the fossil resources. At the laboratory scale, there are several different approaches. One is photoelectrochemical water splitting reaction, and another one is so-called artificial photosynthesis or photocatalytic water splitting reaction. In this field, there are many different fields researchers join. Today, I like to focus our attention on the inorganic solid-state materials using a semiconducting photocatalyst because my major is heterogeneous catalysis. In our project, we produce many different types of semiconducting materials for overall water splitting reaction. And then we apply those materials in two different ways. The first one is photocatalytic water splitting reaction, as shown here. In this case, we use this kind of particulate photocatalyst. And another way is the photoelectrochemical water splitting reaction. In this case, we construct this kind of photoelectrode. Frankly speaking, if we like to achieve higher solar to hydrogen energy conversion efficiency at a laboratory scale, this photoelectrochemical system is easier. However, if we consider a large-scale application, we have to face a serious problem to extend to a wide area in this case. On the other hand, in the case of photocatalytic reaction, it is more difficult to improve the efficiency. However, if we like to extend to a wider area, this method is much easier. So today, I'd like to focus our attention on the photocatalytic water splitting reaction, then photocatalyst sheet and water splitting panel. Therefore, our target reaction is very simple. We like to split pure water into hydrogen and oxygen using solar energy on heterogeneous photocatalysts. Of course, the motivation is as follows. If hydrogen is produced from solar energy and pure water on a large scale, it can be a clean and sustainable energy carrier as well as chemical resource. However, from the viewpoint of technology, the situation seems to be more serious because we need to produce solar fuels on a large scale at a low cost in the near future. Now let me move to the next part, particulate photocatalyst for water splitting reaction. In this case, I will discuss about aluminum-doped strontium titanate. Here I show that some different types of photocatalysts, powder photocatalyst, and this is a UV responsive photocatalyst, and these are the visible light responsive photocatalysts. But first I will discuss on this type of photocatalyst. Okay, here I shows that preparation procedure of our aluminum-doped strontium titanate photocatalyst. In this case, we use a so-called flux method using a strontium chloride. And the ratio of strontium chloride, strontium titanate, and alumina is 10 to 1 to 0.1. And then this mixture is calcined in air at 1423 Kelvin for 10 hours. By this treatment, we obtain this kind of small particles. The particle size is a few hundred nanometers, and the amount of doped aluminum is about 0.1 atomic percent. Then we use this type of particles as a photocatalyst by properly modifying for overall water splitting reaction. Here I show the wavelength dependence of the apparent quantum efficiency as a function of the wavelengths. And in this case, if we consider a so-called internal quantum yield, I mean that if we evaluate the quantum yield based on the total photon number, what was truly absorbed by our photocatalyst, we believe that in this region, the internal quantum yield is very close to 100%. That means that it is possible to split pure water into hydrogen and oxygen using particulate photocatalyst with a quantum efficiency of almost unity. But our goal is not to develop this type of efficient photocatalyst, but we like to apply these types of photocatalysts to a wide area to produce a large amount of green hydrogen. To achieve this kind of large-scale application, there seem to be several different ways, but probably the most simplest way is to construct this kind of water splitting panel. To construct this kind of water splitting panel, we need to fix our particulate photocatalyst in 2 dimensions. We call such kind of system as a photocatalyst sheet. Now let me move to the next part, photocatalyst sheet and water splitting panel. Again, let me start with the aluminum doped strontium titanate. In this case, the preparation procedure is much easier. After modification of our aluminum doped strontium titanate for hydrogen and oxygen evolution, we mix that photocatalyst with a nano-sized silica particles, then in an aqueous solution, then just spray coating on a frosted glass plate, and then calcined in air at about 90 degrees C for several hours. That's all. And then this is a 500 milliliter beaker just filled with distilled water without any electrolyte. If we put this beaker outside under sunlight, or if we irradiate by solar simulator, we can get this kind of bubbles coming out. This is a bubbles of hydrogen and oxygen exactly in 2:1 ratio, which is splitted using the UV light included in sunlight. And this is a cross-sectional view of this type of photocatalyst sheet. As I said, we used a frosted glass plate, as shown here. This is a 10 micrometer scale bar, and these white particles are photocatalyst particles, and this dark gray part is nano-sized silica particles. Then we magnified more by using STEM images. This is 10 nanometer scales. In this case, this black part is the photocatalyst particles. In between, there exists nano-sized silica particles. This particle size is about 10 to 20 nanometers. In between, there exists this kind of voids. This void is actually filled with distilled water, and the evolved hydrogen and oxygen molecules are dissolved into this distilled water under supersaturated conditions. The reason that the bubble was not formed at this space is that this space is too narrow to make a seed of bubbles. Therefore, that's up to on the surface layer of this photocatalyst sheet, we have a supersaturated hydrogen and oxygen molecules. Using this kind of photocatalyst sheet, we constructed a water splitting panel. In this case, a 25 centimeter type 25 centimeter, using 0.4 gram of photocatalyst and 0.9 gram of photocatalyst. This is a side view. Here we have a photocatalyst sheet, and this is a gas outlet, and this is a water inlet. Water is very, very slowly introduced into this water splitting panel, and the thickness of the water layer is only 100 micrometer, 0.1 millimeter. This is a real structure of our water splitting panel. In this case, we irradiated by UV LED at 365 nanometers. And I hope that you can see that small bubble is going up quickly and then go outside through this gas outlet. I should say that the rate of the water splitting reaction in this case was exactly the same when we have millimeter thickness or centimeter thickness of water layer. That means that 100 micrometer thickness of distilled water is enough to effectively split water into hydrogen and oxygen. Now let me introduce a little bit different types of photocatalyst sheet. In this case, we use 2 different types of photocatalyst. One is for hydrogen evolution, another one is for oxygen evolution. That means that we use a so-called Z-scheme overall water splitting reaction to form the photocatalyst sheet. The preparation procedure of this photocatalyst sheet is also not so much complicated. We just mix these 2 different types of photocatalyst powder in an isopropanol, then just drop casting on a glass plate. Then after drying, we get this kind of mixture of 2 different types of photocatalysts. The thickness is at most about 10 micrometers. After that, we deposit electron conducting layer, in this particular case, gold or carbon, by sputtering or evaporation. After annealing to fix this layer to the photocatalyst, firmly, we push another glass plate on top of this layer. In this case, this glass plate has a carbon tape, double-sided carbon scotch tape. Then if we peel off this glass plate, we can get this kind of structure. And that means that we produced a photocatalyst sheet on the glass plate. In this particular case, the size is 3 centimeter times 3 centimeter. If we observe the surface of this photocatalyst sheet, this is the top view of the SEM image. As you see here, that this is not really so good organized. This red dot indicates the oxygen evolution photocatalyst. This green dot indicates the hydrogen evolution photocatalyst. And in this particular case, we use a gold as a contact layer. So this is the whole structure of our system. That is not really so well organized. However, if we put this photocatalyst sheet in a distilled water again, then irradiated by solar simulator, we obtain this kind of bubbles coming out. Again, this is the bubbles of hydrogen and oxygen, exactly in 2:1 ratio. And the quantum yield at around 420 nanometers for the more than 30%. And the solar to hydrogen energy conversion efficiency was about 1.2%. Okay, now let me move to the next part. Our recent attempts for the construction of a prototype solar hydrogen production system. In this case, we also again use this aluminum doped strontium titanate. Here I show the whole structure, a schematic structure of our solar hydrogen production system. These are our water splitting panel, then evolved hydrogen and oxygen mixture, including the saturated amount of water vapor is carried to this gas separation unit. It includes the gas separation membrane. And actually, we constructed that about 100 square meters light receiving area at the Takioka Research Facility of the University of Tokyo. And here we have a small hills, and on top of that, there is a flat places, and there we constructed this kind of system. In this case, we used the 1600 units of the water splitting panel. The size was 25 centimeter times 25 centimeter to cover 100 square meters. In addition to that, here we have a gas separation unit. It includes the gas separation membrane. And this is a bubbles of hydrogen and oxygen, which is evolving before introducing into our gas separation unit. In this particular case, the rate of gas separation was about 3.6 to 3.7 liter per minute. Okay, now let me summarize and let's discuss a little bit further our development of solar fuels. Here I show our image of future implementation of this new technology into the real world. Actually, we like to make our unit in a real system to the 10,000 square meter, 1 hectare. That is 100 times wider area than our prototype system. And in this area, we have only one gas separation unit. And also, we like to achieve about 5% solar to hydrogen energy conversion efficiency. This is a value that our collaborator industry people evaluated, that if we can achieve this number, that will be the time to consider the commercialization of this new technology. Then problem of the green hydrogen, which is produced from solar energy, that is obviously intermittent generation. So it is not really a good idea to store this green hydrogen on a large scale at a high pressure. Therefore, we like to store this hydrogen on a small scale. Then we like to immediately transform this hydrogen to some other materials which are more easily stored and transported, more easy transportation. For example, that the methyl cyclohexane produced from toluene, or methane from carbon dioxide, or ammonia from dinitrogen. To do that, we need the carrier, the DSS operation, daily start and stop operation. To achieve this kind of catalytic reactions, we need a thermal catalyst, not a photocatalyst, a thermal catalyst, which is active at around 200 degrees C or even below. Actually, even now that to produce a MCH or methane, we have such a kind of catalyst. But in the case of ammonia, Recently in Japan, that some group has been developing such a kind of photocatalyst which works at around 200 degrees C. So we are now collaborating to carry out the DSS operation of ammonia production. But here, let me just introduce the case of the methane formation. Actually, this is a system that we have constructed for the European Innovation Council's Horizon Prize contest on fuel from the sun artificial photosynthesis. Fortunately, we won this contest, and here I show that our system. We have here the water splitting photoreactor. Then here we have a gas separation unit, and then pure hydrogen and carbon dioxide mix, and then this is a methanator which works at about 200 degrees C to generate methane. And this is a real system. And actually, in this case, we allowed to use 5 meter times 5 meter total area. And this is a water splitting panel. And here we have a gas separation unit. And this is a methanator to produce methane. And this is a methane container bag. In this case, at the 3-day test run at the European Commission's Joint Research Center site in Spura, Italy, carried out. And this system is totally computer controlled. And for 3 days, this system was perfectly worked as a DSS operation. Then that here I show that our future development tasks which we should do. That's the most important point is that the development of more efficient photocatalysts and the mass production method of photocatalysis and the more stable photocatalyst sheet and cost-effective water splitting panel. In addition to that, we need to develop more efficient membrane for hydrogen separation and efficient pressure reducing pump for hydrogen separation. And another important point is, of course, rigorous safety verification. But among these tasks, we believe that the development of efficient photocatalyst, which has a solar to hydrogen energy conversion efficiency more than 5%, is the most significant issue. Other problem will be solved in will not take so long time to solve these problems. Okay, thank you very much for your kind attention.
Now may I invite Mr. Hanson to do sharing. So please, Mr. Sun.
Thanks to the VinFuture for the invitation to present our work in this webinar. And today, I will try to give you a quick introduction about the energy transition in Vietnam and what could be the role of the green hydrogen in the near future, and also furthermore, within the national context. Let's start first with the agenda, with the outline of the presentation. I will cover, as you see, energy transition in Vietnam, and then why green hydrogen would be an alternative fuel for the energy transition. What could be the potential opportunity and challenges to the green hydrogen development in Vietnam, as well as the what we can expect with the research and development R&D, and how we can bring the local capacity to fit in with the future demand, and to the end, some key finding and the next step that we expect to see from the government of Vietnam. So first, we learned a lot about like a topic like decarbonization, net zero. Vietnam has committed the net zero in COP26 in Glasgow. But let's look back at the picture. When you compare between the energy consumption and the GHG emission of the country, Vietnam is still in the energy poverty zone. I mean that the consumption of the energy in the country is still low as compared to other countries. However, it also stays in the potential high carbon dioxide emissions per capita. due to the population of the country and as well as the economic growth of the country. It means that the energy demand in Vietnam will continue to grow and also the GHG emission. And that's why the government considered to quickly right now start to commit with the net zero target by 2050. And as we know that energy sector is the most contributor to the GHG emission in the country. And therefore, the decarbonization of the energy sector should be a priority for the country to achieve the net zero goal. If we look back at the energy transition before 1859, everything is just based on the traditional biomass, but with the industrialization, what they call the revolution number 1, then everything changed with the coal and oil and gas and nuclear. And only recently, starting from 1960, then renewable energy started to be like to appear in the energy mix of the world. And from 2020, fossil fuel has been kind of like dominance in the global energy mix, and all countries start to look at the renewable energy as the solution to deal with the both the energy security issues as well as the climate change issue. Vietnam, anyway, is the a country is quickly fitting with the trend of the world. Vietnam is among the top countries, the high share of the renewable energy. If you compare with other like developed country, Germany, Spain, United Kingdom, because Vietnam has the high potential of the hydro power in the country. But with the limitation of the hydropower development in the near future, then other variable renewable like wind and solar would take that role. And Vietnam has consumed more solar energy and so as compared to about 5-6 years before. However, the problem to Vietnam is that due to the development of the infrastructure to support the integration of the renewable energy like wind and solar into the power system. So the curtailment of the wind and solar has been occur more frequently, and that would be the big issue that the government have to deal with in the coming 5 years and further. The challenge to the energy transition, as analyzed by the expert in the world, at first the world didn't rely on coal, and especially with the Asia Pacific area, and that's why the solution would be to expand the renewable like wind and solar, biogas, and also we need to consider gas as the bridge technology is its intermediary solution to replace coal. Volatility and grid stability also are big issues to the developing country, given the energy security issue, and therefore the source of flexible sources and a lot of power sources which could be mobilized with the fast starting or dispatchable should be considered and win in the near future. And last but not least, the flexibility at applying of the use the fluctuating hydrogen mixes in the gas network would be important, because the Vietnam already have the gas industry exploration and processing, and that's why how we use the existing infrastructure to adapt with the energy transition process in the country is important. So we can see clearly from the presentation of the two professors before that hydrogen somewhat, especially the green hydrogen have a very important role and good future for the country, because it can help to transform the energy created from the renewable energy like wind and solar into like hydrogen, or with the methane or ammonia as the fuel to replace the conventional fossil fuel, and can be used for both the transportation as well as other application in the industry and the residential purpose. With Vietnam, the government already identified the pathway for the green hydrogen with a lot of like strategy and policy. As you can see here, like Resolution 55 as the key orientation document guiding the use of hydrogen, the green hydrogen or clean hydrogen in the country, following the global trend. The recent decision 500 approving the power development plan number 8 has mentioned that transition to hydrogen fuels is important, but also under the condition that the technology is commercialized with the reasonable market price. And the government of Vietnam also approved the energy master plan with decision number 893. This is highlight the role, important role of hydrogen within a lot of application like power generation, transportation, industry, civil and commercial building, and so on. So we also see a lot of other like policy documents, strategy, and so on. But I just want to highlight the 3 key documents that we can see clearly that how hydrogen could be developed in Vietnam in the future. With the power development plan, we can see clearly that how the power sector would be developed to fit in with the net zero emission through the reduction of the dependency on the coal thermal, and also using the natural gas as the immediate fuel for Vietnam during the energy transition. And here we also see the hydrogen conversion is important to replace natural gas. Renewable energy is also important, as we know that the renewable energy would be used to generate the hydrogen, the green hydrogen, when we have more capacity of the wind and solar in the country. And of course, with the storage, we learned from Professor Nigel, Brandon, that there are a lot of like potential solution with the storage, like and also application with the hydrogen in the way that we can both storage the energy, but also from that we can generate the power, and we can use that for different purpose like industry and transportation. So just look at the graph. It's very simple that at the moment Vietnam rely a lot on coal and gas, and we are developing the renewable energy for the future. And with the excessive capacity of the renewables in Vietnam, then we can expect that we can generate the green hydrogen for the country to replace the coal and the gas. And that would be the projected future for Vietnam until 2030 and further to 2050. Some study have made some assessment on what could be the potential for the green hydrogen for Vietnam, as you can see on the left side of the slide. And with the existing gas industry infrastructure in Vietnam, it has been proved that the hydrogen could be mixed with the pipeline gas, or the country can consider to build a new dedicated hydrogen network to fit in with the new demand if needed. But everything showed that we here in Vietnam we have both the potential and also the capacity and the infrastructure somewhat available to work on the green hydrogen. But the challenge here is that we see that hydrogen is not the solution for everything because a lot of limitation, especially with the price. And you know that lacking of the sufficient incentives to make the green switch from the conventional fuel to green hydrogen would be the key challenge to the country, and also even for the developed country. For instance, we can see that with the EU emission trading system, ETS, the green ammonia is 2 to 3 fold more expensive than the gray hydrogen, and of course, it's still much more expensive than the conventional gas at the moment. And also, we have to deal with the big challenges according to the cycle losses for power generation, and also how we can bring the new infrastructure to really deal with different purpose that economically used for the future, because that would be the stranded asset if we just build the infrastructure or the hydrogen infrastructure for everything, for all the demand, and then it will be a waste of due to the low efficiency, low usage of that system. And this is some illustration on how energy losses would happen in either the green hydrogen production from the electrical energy, or it could come from the conversion and the shipping of the hydrogen related product. Some study have been conducted to show what could be the strength, weaknesses, opportunity, and threats to the green hydrogen energy system development in Vietnam, as you can see here. And usually we can see that with the strength, we just have a few with regard to the available technology, with the potential or the policy in place. But there are a lot of weaknesses, mean that how we can realize those policy into something like roadmap strategy and specific policy and the incentive mechanism to support the development of green hydrogen in the country. Of course, they come with the opportunity like funding, like exportability, as some private company has realized recently, and they had asked to win some factory for green hydrogen. But funding is also both the opportunity, but also the threat to the development of the green hydrogen in the country, because you have to see that people usually the government people expect a lot about how to develop the policy system with the perfection, and therefore they would come with a delay in the policy development, and that would have some impact on the development of the green hydrogen industry as a whole. And production costs also a challenge, and how we can bring the capacity, resources on financial, human, technical to fit in with the development of the new industry. And here, I just highlight one study conducted back in 2021 that they reviewed the process with Vietnam, the capacity of Vietnam with regard to the green hydrogen industry development. And you can see here that beside the domestic energy capacity, the society development, this is how we can convince the society to accept the new fuel, the new way of using fuel, and also with depending on the national economic condition. But R&D capacity is very important factor that can push up the development of the industry in the country. And we just learned from both Professor Nigel Brandon and Professor Kazunari Domen about the process, and a lot of progress, but it depends a lot on how Vietnam put in the investment into the R&D to bring the R&D capacity in the country. And of course, about technology, we learned a lot today, and this is just a summary of the technology available at the moment with different like solution, with different combination, and the progress so far. So to take a overall look at what happened in the country and what we can expect. In general, Vietnam and some other nearby country have similar challenges and potential, and therefore we can see clearly that because of the government commitment on the net zero, so they come with a high interest in the development of the hydrogen industry in the country, but creating the enabling environment for green hydrogen development in the country is also a big challenge, and policy need to be developed carefully with the consideration of the local capacity, infrastructure need, and as we can see that it will require a lot of financial support and the investment on this one. And the investment on the R&D is important given the existing knowledge and the capacity in the oil and gas industry in the country. I mean that Vietnam not started from scratch. We have something already available to continue with the for development of the hydrogen in the future. And last but not least, the international support and collaboration on technology transfer and financing are needed. And for our program here, this is funded by the United States, the USAID. We are working with the Ministry of Industry and Trade at the moment to try to identify the gap and try to like advise on how to like bring up the capacity as well as the policy with different topics, including the green hydrogen. So that's all of my presentation today. Thank you for your attention. Yep.
So thank you very much, Mr. Sun, for your sharing. We're really happy to see that Vietnam has high-level commitments and is very much interested in green hydrogen and trying to achieve net zero. So thank you very much. So thank you very much for all the three speakers, Professor Brandon, Professor Domen, and Mr. Sun, for sharing your exciting developments with us and giving us a lot of confidence and hope for net zero to come. And of course, there are still a lot of challenges, but we are really so happy to see so many very promising and exciting developments. But it also pins down to the fact that we need to really have other things to overcome the hurdle, like the infrastructure, as has been mentioned, maybe the size of the electrolyzers, and most importantly, if we want to achieve the green hydrogen economy, the cost of solar electricity or other types of clean electricity must have to come down. So with that, maybe let's have a little bit of interaction here. So maybe could I ask Professor Brandon first on what do you think are the major challenges? You have achieved a lot already, and you have your spin-off company and a lot of products already ongoing. So what do you think are the major challenges that need to be done in order to really push it further?
Sure. Well, thank you. I mean, I think I say a couple of things. Firstly, as I think was evident in the last talk, hydrogen is a system enabler, right? It's there to play a role in helping the overall energy transition. And therefore, we have to think about it in the system context. So one of the things is not just to think about how we make it, but also how we move it, store it, and use it as an energy carrier, and how that energy carrier interfaces, whether it's with liquid fuels ultimately made from hydrogen, or whether it's with electricity. So I think from a kind of national perspective, whichever country you're in, you have to look at that system context. So that and then the challenge with that system context is that often current policies for how sectors are regulated, whether it's an electricity industry or a gas industry, and how different industrial sectors connect together start to become important as well, right? So that's the kind of high level bit. And then secondly, all of these technologies have to be at scale, and of course they have to be cost effective as they can be. And so we can't ignore manufacturing in all of this, and how we move globally to a manufacturing base that is delivering products at the right scale, at the right as competitive a price point as we can manage is important. In the context of electrochemical technologies, which is what I sort of focus on, the only electrochemical technology manufactured at a global scale today is the lithium-ion battery, which of course has received huge investment off the back of the interest in battery electric transport. And the cost down that we've seen in that reflects that manufacturing scale. I think there are similar opportunities for cost down in electrolyzers or in fuel cells or in flow batteries or whichever technology we choose, but it needs that level of global investment. So there is this interface then between market demand, signposting for that demand, and the investment in manufacturing. So I think those are the two things I'd highlight, right? Systems context and manufacturing investment to deliver a product at scale. I think there of course will continue to be innovations, and we heard about some really exciting work on solar water splitting, and we'll continue to innovate, but this is also about getting to volume. So I'll leave it there.
Yeah, thank you, Nigel. So may I now turn to Professor Domen? So you have give us a very promising technology showing us all these photocatalyst plate and solar panels and large scale So what do you think is the major hurdle that will really slow down the process? Or what would you like to see to speed up the development of this solar hydrogen technology that you talk about?
Okay. At present, I believe that the major route to produce a green hydrogen is solar or wind power, electric generation, and electrolyzer system. And of course, it is already almost commercialized, but our approach using photocatalyst and direct water splitting reaction is still at a laboratory level, so that the TRL level is maybe at 2 or 3. So we need the most important hurdle to realize that such a kind of hydrogen production system is to develop the photocatalyst which can achieve more than 5% solar to hydrogen energy conversion efficiency. Once it will be achieved, I believe that the other issues will not take so long time, because we are now collaborating with many industry people, and those industry people have their own technology to solve those problems. And but as Dr. Hadon Song said that Vietnam is a rather energy poor country, but Japan is also energy poor country. So in any case, we need to collaborate with some other countries, such as Australia or United States, or maybe EU or Near East countries. And actually, we have already started to do some collaboration with those countries' researchers. And then that's eventually that's the most important point, is how to produce green hydrogen at a low cost, which eventually could competitive to fossil resources. Otherwise, I consider that many countries will keep using the fossil resources as far as the cost of those fossil resources is lower than the other green hydrogen or other energy resources, renewable energies. So important is that to start a collaboration, and then that try to make a lot of effort to reduce the cost. I believe that for example, in Australia or in the United States, there are a good place to generate green hydrogen at relatively low cost. Yes, that's all. Thank you.
Thank you so much. Yeah, indeed, the cost of hydrogen is very important. I think right now I read some reports that actually electrolytic hydrogen now costs about $5 to $7 US dollar per kilogram. And I think they have a plan to really look forward to eventually moving towards $1 US per kilogram. And of course, Professor Nigel Brandon also shared with us some of the sort of cost of hydrogen in UK as well. And so then maybe my next question to Mr. Sun is that Vietnam, and I'm really glad to see all the very positive commitment of Vietnam government into net zero and become very interested in green hydrogen economy. So how would you see it in terms of cutting down on the cost of hydrogen to make it really viable for people to be convinced to use it? So please, Mr. Sun.
Yeah, we know that the key challenge to the transition to green hydrogen would be, first is the technology, and the second would be the cost factor. And as long as the green hydrogen not competing, not able to compete with other conventional fuel like natural gas and LNG, for example, would make it very difficult for the country to develop at the scale, because you know that at the moment the government still maintain like more stable and affordable energy price, so that the poor people can still enjoy the energy, a good energy at the price at the affordable level. But with the adoption of the green hydrogen, the cost of energy for different applications could be very high and no more competitive, and that's why we expect to see, not in a few years from now, but probably from now until 2030, and there will come the revolution with the technology, with the more effective and with the more competitive technology. This is commercializable, and based on that one, then green hydrogen could be a potential fuel to replace coal and the natural gas in the future.
Yeah, thank you so much. So I think it's time for us to pass back to the Secretariat. So thank you very much. So please.
Well, thank you very much to our panelists for a very engaging panel reflection. And also thank you so much to Professor Vivian Yam for your incredible guidance as well. And now let's give our panelists a well-deserved break of 5 minutes after their incredible dedication to the webinar. And in the meantime, I would like to invite you all to keep watch for a short tutorial video. And this video serves as a process on guiding you on how to submit your nominations to the VinFuture Prize. Please take a look, and we will reconvene shortly after.
Greetings from the VinFuture Prize. Please find instructions for the nominator following these steps. To begin, you can access the nomination portal at online.vinfutureprize.org/nomination. Alternatively, you can scan the QR code on the screen to open the nomination webpage. On this webpage, you can download the instructions and the endorsement letter template. In the instructions, you will find the complete nomination form where you can draft the nomination at your convenience. Afterwards, you can copy and paste draft into the online portal. Please click on Sign Up, and upon successful registration, you can simply use your ID and password to log in. After logging in, please click here to start a new nomination form. Subsequently, you can see 7 content tabs on the nomination form to begin the nomination process. On the first tab, please select the prize category as well as the type of nominee, whether it is an individual or a group of nominees. Then, click the Start button to proceed to the second tab, and we would like to draw your attention to tab number 5 and tab number 7. On tab number 5, your evaluation, you are invited to give your evaluation of the nominee's invention, including its groundbreaking discovery, scientific fundamental knowledge, specific approach, uniqueness, and advancement. Additionally, you are required to clarify if the invention can be transferred to a product and highlight its most significant socioeconomic impacts. This includes the number of beneficiaries, such as people, countries, and continents. Please explain how you believe this invention has or will potentially transform the everyday lives of millions, if not billions, of people. Next, please provide information on the history of the invention, such as when and how it started, and who else, except the nominee or nominees, was involved in initiating or contributing to the invention. About tab number 7, supporting documentation and evidence. There are several important documents that the nomination portal and form require. We would like to draw your attention to 3 critical items. The first one is the CV of your nominee, or the CVs of your group of nominees if you are nominating a group of people. The second important item is the endorsement letter. 3 endorsement letters are strongly encouraged, but 1 is mandatory. The third one is the additional form of nominees. Please provide as specific information as possible. Additionally, you are strongly encouraged to include any valid intellectual properties, publications, patents, or other supporting documents that provide evidence for the nomination. Finally, after filling out and providing all the content in the 7 tabs, please click on the Submit button at the bottom of the page to submit your nomination.
Well, ladies and gentlemen, one of the most highly anticipated segments, the Q&A segment, is now upon us. And just before this segment started, we actually received several signals from several members of the audience who would like to directly connect and interact with a member of our panelists. And the first one who would like to connect with Mr. Ha Dang Son is Dr. Da Dang Chuang. Can I please have Dr. Da Dang Chuang in the audience? Would you, what questions would you like to send Mr. Ha Dang Son?
Yes, so thank you for your inventions. I would like to ask why some companies like TGH having company or a company in the Belgium, they want to invest money to build the to build green hydrogen plant to produce green hydrogen.
Dr. Ta Dang Chuang, I sincerely apologize. I have to interrupt for like a little bit. Can you please turn on your camera just so it can make for a more interactive session with Mr. Ha Dang Son, please?
Sorry, my camera is broken, so I have to speak. Just speak, okay?
Okay.
Okay, so my question is, some companies like TGH Shopping Hydrogen and company from the Belgium, they want to invest money in Chavin province in Vietnam. So why not Chavin? Why not other provinces like Ninh Thuận or Binh Thuận or Cà Mau? So this is my question. What makes Chavin become special for the investors?
The answer is quite simple because the investment decision will be made by the private sector they all, and when they consider to make a decision on the investment, they consider different aspects beside the availability of the renewable energy. So you also have to consider the relationship with the local authority, the availability of the project is somewhat agree on providing the power for the green hydrogen. My understanding, the reason why the first green hydrogen plant would be wind in Chavin because there are other wind and solar projects available in the nearby provinces like Mianche or Sokchang. It's still in the curtailment. I mean that they cannot sell the power to the national grid, and that's why green hydrogen would be considered as the solution for them to secure the income and also the how to say the payback on investment for such the project, and such kind of negotiation and agreement would be dealt by the private sector only. I don't see any reason for the government to have any involvement in that negotiation.
Yes, thank you. Another question I want to ask. So I see the bananists talk about using the excess electricity to produce green hydrogen, but I think it's quite ambitious, because it is low capacity factor to produce green hydrogen. So I think just build a power plant, a renewable power plant for producing green hydrogen to export is more economical compared to the former one.
It depends on what could be the price that the buyer want to buy. So as you can see is that, yes, I agree with you that the efficiency of the conversion from the power to the green hydrogen and then convert it back to as a fuel, to for instance generate the power or serve as for the different purpose may be ineffective or maybe too expensive. But given the condition at the moment with the Vietnam, where the cost of the energy production may be still low, then if you compare with the developed country, maybe the price of the green energy would be acceptable to those countries. I don't know the price in Japan. I don't know the price of the green hydrogen in UK, but that would be, as I learned, that there are a market for the EU country, for some committed country, developed country, that they can accept to buy the even expensive green hydrogen to fulfill the commitment of decarbonization and net zero. Then, therefore, we have the market. Then there will be the business.
Yeah, thank you a lot for your answers. Thank you.
Thank you so much to Mr. Ha Đăng Sơn and also to Dr. Tạ Đăng Thương for sending in your questions. The next signal that we received from another member of our audience is Mr. Ziyi Zhang, who would like to send in questions directly to Professor Kazunari Domen.
Okay, thanks the organizer for organizing this wonderful event and also all of the speakers. I have two small questions for Professor Domen. And actually, I'm not working for the catalysis, many thermal catalysis. I noticed that you mentioned one of the two numbers. One is STH, solar to hydrogen. This should be above 5%. Another is when you get hydrogen, you store it and convert hydrogen to some other fuels like methanol, and you mentioned that temperature should be below 200 degrees. Could you please give me a little bit more details of these two numbers? Why?
Yes. Okay. I'm not saying to conversion to methanol, because in the case of methanol, it is not so easy to carry out a DSS operation. In the case of methanol formation, we need to store a large amount of hydrogen, or maybe we need to combine with a methane reforming reaction, because of the methanol formation reaction, it has to carry out continuously. You understand? But what I would like to say is that if we can make that such kind of methane or ammonia at about 200 degrees C or even lower temperature, then that we can transform hydrogen and, for example, carbon dioxide into methane, and at intermittent hydrogen production. So in that case, we don't need to continuously operate our reactor. We can stop. If that's the hydrogen evolution is stopped, we can stop the reactor of methane formation. Or if we can make ammonia synthesis catalyst, which works at about 200 degrees C, then in that case, if we mix hydrogen and a little bit larger amount of nitrogen, then increase the pressure at about 30 bars, then one pass conversion, we can reach to the almost the equilibrium condition. Then that's we can consume almost all hydrogen by one pass conversion. That is very much different from the conventional Haber-Bosch type ammonia synthesis reaction. So such kind of new type of reaction system will be necessary to produce the some energy carriers or some other types of solar fuels to produce at a low cost. That is my point.
Okay. Regarding this, pardon, I still might be asking a little bit more regarding this reaction temperature, because I don't know because you mentioned this temperature in your slide. Then if the temperature is too low, maybe the kinetic the reaction rate will be too slow. So you set up this temperature is because of the thermodynamic or kinetic issue reason.
Of course, the kinetic issue is a very important problem, especially, for example, in the case of ammonia synthesis. We need to develop a high activity catalyst,
Yes.
which works at about 200 degrees C. Yeah. That is now we are collaborating with the other groups, which devise new type of catalyst for ammonia synthesis. So that we believe that their catalyst has some potential to achieve such a kind of high rate of ammonia formation at lower temperature.
Okay. Thank you very much. Yeah.
Yes.
Thank you. Yeah.
Well, thank you so much to Professor Kazunari Domen for addressing Mr. Ziyi Zhang's question. And the next question is actually addressed to one of our distinguished speakers, Professor Nigel Brandon. This question is, storage of hydrogen in massive scale is dangerous. Our member of the audience would be interested to know why not thinking about the smaller units to utilize hydrogen as per Applications Institute.
Okay, thank you. Well, the first thing to say is that we do store hydrogen in large underground caverns already. It's not done for the same purposes, but it's done as a strategic part of, for example, petrochemicals industry. So there are very large amounts of hydrogen and indeed very large amounts of natural gas stored in underground caverns in the US, and also we have underground storage in the UK. So it's, in that sense, it's a well understood technology and can be done completely safely. The difference here is that you would want to use probably fill and empty that store a little bit more regularly than you might do if it's more of a strategic backup to provide hydrogen into a chemical plant. So I think there is no reason to think that we can't deliver that. The question then about the scale of hydrogen storage, I mean, there are going to be applications where it makes sense to store smaller amounts of hydrogen more locally, to move to even things like solid state storage for hydrogen at the length scale of perhaps an individual building or light industrial unit. But yeah, I don't see there's no intrinsic concerns over the safety of storing hydrogen in large amounts in underground caverns.
Well, thank you very much, Professor Nigel Brandon. And to our audience, unfortunately, due to our very limited time constraints, we are unable to proceed with many more questions that you have sent in. But now we will reach our final question, which is addressed to our chair for today's webinar, and that is Professor Vivian Yam. What are the key challenges of the green hydrogen economy? Is renewable hydrogen profitable?
Yeah, I think we heard from the distinguished speakers as well as the government officials on obviously green hydrogen economy is something that's very attractive. But of course, there are a lot of hurdles that we need to overcome, as we have heard, like the systems context, the manufacturing investment, and also whether it's one will be able to do it for in terms of storage and also conversion and many others, like what Professor Domen also mentioned, that we need to achieve higher photocatalyst efficiency in order to be at least above 5% for the conversion STH. And also we heard from Mr. Sun about the infrastructure, right? And also whether this is sort of affordable and whether it will be profitable. Of course, we would love to see that it's profitable. As I mentioned, right now it's like $5 to $7 per kilogram, which is still quite expensive. And there are projections that hopefully it could go down to $1 per kilogram in the next 10 years time, and hopefully we'll cut down on the cost also. But I think the most important thing is at this point, whether it's profitable or not, it's not so important. It's whether we can really come up with the technology with the efficiency and with the interest of investment going in there to make us a better world, right? Because we are really facing a very important, like we want to go to net zero in order to save our world, to save the globe. So I think this is something that's more important. But of course, it has to be affordable. So I guess all the scientists, as well as the government, and also hopefully the investors are working hard towards that in order to help us in terms of the carbonization and coming up with a carbon neutral or net zero sort of economy. So I think this is the most important thing that we as scientists and everyone in terms of the government, the investors, that we need to work together. And as also mentioned, the international collaboration is extremely important. I mean, it's not talking about just one region or one country. I mean, scientists must go hand in hand, and science has no borders. So we must collaborate amongst everyone to make a better world. So thank you.
Professor Vivian Yam, thank you very much for concluding the Q&A segment. Now, as we reached the conclusion of today's webinar, I would like to express our sincerest gratitude to Professor Vivian Yam. Her incredible leadership as the chair of today's webinar has been nothing but truly invaluable. And of course, to our two distinguished speakers, Professor Kazunari Domen and Professor Nigel Brandon, your profound insights have all enriched us all in the audience. And of course, let us not forget our representative of the vibrant Vietnam energy community, Mr. Ha Dang Sơn, for gracing us with his presence. And now, as we come to the end of today's webinar, we would also like to thank to our audience with your incredible engagement in the Q&A session. We would also like to invite our panel that includes our chair, our two distinguished speakers, and our special guests to turn on their cameras, and let's all take a group photo to capture today's very special moment. Well, once again, thank you very much for being a part of today's InnovaTalk webinar, A Green Future of Hydrogen Economy. We're looking forward to seeing you once again in other InnovaTalk webinars from the V-LEEP Future Foundation. Thank you very much and goodbye.